back in section 4.2. We get to work with the second derivative and see how it relates to graphs. So some symbols for the second derivative. You may see f double prime of x. You may see d squared y over dx squared. You might see d dx of f prime of x. You may also see y double prime. So all kinds of different notations. These are just commas in between them for the second derivative. So as far as intuitively what these are talking about, I'm going to just sketch a couple curves. So let's say this is at x equals a and this is at x equals b. If we sketch in the tangent lines, remember the slope of the tangent line is defined by the first derivative. It's talking about the instantaneous rate of change in the curve at that given point. So notice here, the curve has a steeper positive slope at A than it does at B. So here, we know that f prime of A is bigger than f prime of B. So as we move to the right, our slope is getting smaller. Now similarly, if we had, let's say, a curve like this, and again, here's A, here's B, and we talk tangent lines, here's one tangent line, so you can see from this, they don't have to be works of art. These are both negative. A is more steeply negative. It would have a bigger absolute value, so hence be a smaller number than the slope at B. So both of these have that same property, that f prime of A is bigger than f prime of B. So we have sort of the small negative slope in terms of absolute value, big absolute value in terms of negative slope. So f prime of B for both of these is smaller than f prime of A. So f prime is still getting smaller from left to right on both of these. And if we flip those upside down, we get kind of the opposite thing happening. So on this one or this one, and we'll still let A be the point on the left, B be the point on the right. On both of these, f prime of A would be less than f prime of B. So the derivative here is getting larger as we move from left to right. So here's a positive slope, here's a steeper positive slope, so a bigger f prime at B. Very steep negative, more shallow negative, closer to the zero, closer to the positives. F prime at B is still bigger, so f prime getting larger from left to right. So this introduces the idea of concavity. These two would be considered concave down. F prime is decreasing. These two are considered concave up. And you can kind of see that both of these would sort of fit into the letter U in up. That's one way to remember it. So concave up, think of a cup. So if we're asked to look for intervals where we have something that is concave up and concave down, we need to look at the second derivative. So we'll start with f of x is e to the opposite of x. Well, then f prime of x is minus e to the minus x. F double prime of x, opposite of e to the minus x, which would flip it back positive on the coefficient. So e to the minus x. So we're looking for intervals where this thing is positive, negative, or 0. This can never equal 0. Remember, this is also equivalent to 1 over e to the x. Positive base raised to a power is going to kick out a positive number every time. So this is positive all the time. This is always greater than 0. So for all of the x, therefore, if the second derivative is positive, this is concave up. And hopefully you remember from your college algebra days what e to the minus x looks like. So it's just the e to the x graph, but reflected about the y-axis. So it is indeed in that concave up type of shape. Let's see. Look at g of x is 1/3 of x cubed. So g prime of x, 1/3 by 3x squared. Do a little cleanup there. And we have x squared. G double prime of x is 2x. So now we want to think of where this is concave down, where this is concave up. We have a positive. If we have a positive times a negative, that would kick us over to a negative. So all of the negative values, which occur on negative infinity up to but not including 0, we have g double prime of x less than 0, so concave down. And on 0 infinity, g double prime of x is positive, greater than 0, therefore concave up. All right, so I'm going to have you all try the same thing. You're going to find intervals where we are concave down or up. And we'll use some of the examples your author uses. So we'll try out f of x is opposite of e to the minus x. We'll try out g of x is the natural log of 1 over x. That will give us a chance to play with the chain rule as well. H of x will try out as x to the 1/3. So go ahead and pause it, see if you can find the intervals for these three. Welcome back. So our first one, we start by finding f prime, which brings us back to e to the minus x, and f double prime of x then is minus e to the minus x, so we're back where we started. So this is equivalent to saying we have -1 over e to the x, so a negative over something that's always positive. This is always negative, so f double prime of x is always less than 0 for all x. Therefore, this is concave down on -infinity, infinity. Our g of x, we'll do a little substitution. We'll let y equal natural log of u, and u equal x to the -1st. 1 over x is the same as x to the -1st. So dy du, it's 1 over u, du dx is minus x to the -2. So dy dx is 1 over x to the -1st times minus x to the -2nd. Actually, that one I don't want the... Didn't want the -2 outside there. It means something different. Okay, so dy dx, reciprocal of x to the -1st is x to the 1st. And then we have a minus x squared down here, so -1 over x, which is minus x to the -1. So then that is our g prime. So g double prime of x is then the derivative of this, which would be negative by a negative kicks us over to a positive. Subtract 1 from the exponent. 1 over x squared. This is undefined at 0, but that's okay. The original is also undefined at 0. Because in the original, we're part of the argument of a logarithm, we don't care what's happening with negative numbers. That's outside of our domain. So with positive numbers, square positive, you get a positive. Positive 1 over some other positive number is always positive. So g double prime of x is greater than 0 for all x greater than 0. So this is concave up on 0, infinity. And finally, h of x, which was x to the 1/3 power, h prime of x, 1/3 x to the -2/3, so 1/3 minus 3/3. 1 and 3/3 are the same. H double prime of x, -2/9 x to the -2/3 minus 3/3 is -5/3. So h double prime of x is -2 over 9 times the cube root of x to the 5th. So here, raise a negative to an odd power, you get a negative. Cube root of a negative is a negative. Positive by a negative is a negative. Negative over negative is a positive. So on -infinity, comma 0, we get a positive. Therefore, concave up. If we have a positive to any power is positive. Cube root of a positive is positive. Positive by positive is positive. Negative over a positive is negative. So on 0 to infinity, in other words, positive numbers, our output for h double prime of x ended up negative, therefore concave down. So we had split behavior on that one. So we've already said that negative means concave down, positive means concave up. There's one other type of number that is neither negative nor positive. In fact, there's only one number with that nice pretty property, and that is our friend 0. So if f double prime of c is equal to 0, x equals c is a possible inflection point. So inflection point means we're changing from concave down to concave up, or vice versa, concave up to concave down. The reason I say possible inflection point, why it's not guaranteed, is that there are some graphs that will be, say, concave up like this one, and then sort of just flatten out, but then return to being concave up instead of switching to concave down. That is definitely possible. That does happen. So that brings us to the idea of the second derivative test. So if there exists a horizontal tangent line at x equals c, and f double prime of c, we'll just do a greater than 0, and you can create your own definition for what happens with less than 0. So we have a horizontal tangent line at x equals c. So we have some type of curve happening, and here is point C, and not the graph itself, but the tangent line has a horizontal slope. Further, we've said that on the graph, second derivative is positive. What that tells us, that means we are concave up. In other words, we have that cup shape. So it must be coming through this way. So that means that this point x equals c is a local minimum. Flip it around and you'll have a local maximum. So then they have us work on doing a sketch based on sort of finding critical numbers, local extrema, and concavity. So let's go through this with f of x is, we'll go with 1/4 of x to the 4th minus 1/3 of x cubed minus 3x squared minus 2. Take a second, pause it, and find the first and second derivatives, and then we'll run through the rest together. Okay, welcome back. F prime of x 1/4 of 4, x to the third, minus 1/3 by 3, x to the second, minus 3 by 2, x to the first. And then derivative of a constant is always 0. And we'll do a little cleanup on that before we go to our second derivative. So f prime of x is x cubed minus x squared minus 6x. F double prime of x then, 3x squared minus 2x minus 6. All right, so the one thing we'll look for, critical values, sometimes called critical numbers. Those, remember, come from f prime. So we'll set f prime to 0. And this one is solvable just by factoring. So critical numbers, x equals 0, x equals 3, x equals -2. Now we're going to use the second derivative test on these to determine if they are local mins or local maxes. All right, so recall that f double prime of x from the previous page, 3x squared minus 2x minus 6, and our critical numbers, we had x equals 0, x equals 3, x equals -2. All we need is the sign from each one of those. So f double prime of 0 is -6, so that's concave down. So we had a horizontal tangent line and we're concave down. That means x equals 0 is a local max. F double prime of 3. Let's see, we have 27 minus 6 minus 6, which is positive, so that is concave up. So horizontal tangent line, but concave up. X equals 3 is a local min. Local is sometimes referred to as relative as well. And f double prime of -2. Let's see, we have 12 plus 4 minus 6, which is positive, so concave up. Horizontal tangent line, concave up. This is also a local min. Something else they can ask us to do, again, we're continuing with the same problem. Find possible inflection points. For inflection points, we'll look for where the second derivative is 0. So 0 is 3x squared minus 2x minus 6. That one, just go to quadratic formula for that. So x is equal to 2 plus or minus square root of b squared is 4, minus 4 times 3 times -6, all over 2 times a is 3. So x is 2 plus or minus square root of 76 all over 6. That has 4 as a factor, so we'll pull a 2. And let's see, a quarter of 76 is 19, all over 2 by 3, so x would be 1 plus or minus root 19 all over 3. So those are two possible inflection points. To determine if they are indeed inflection points, we're going to sort of break up the number line the way we did with the first derivative test and do a little sign test. So 1 minus root 19 all over 3, approximately negative 1.1. 1 plus root 19 all over 3, x is approximately 1.79. Should really round that to a 1.12. So I just need a guinea pig from each interval. Again, a little reminder, f double prime of x here, 3x squared minus 2x minus 6. So something to the left of that, we can use, I don't know, a negative 5. And in between a 0, and to the right of the 1 plus root 19 all over 3, let's do a 5. So f double prime of negative 5, that lands us on 85. It's greater than 0, so concave up. F double prime of 0 is negative 6. That's less than 0, so concave down. So this one is indeed an inflection point. We change from concave up to concave down. Now we see if we go from concave down back to concave up. If we do, this also is an inflection point. But we don't know that until we test it out. Sometimes it is, sometimes it's not. F double prime of 5 landed us on positive 69. That is greater than 0. So we are concave up on that one. So both were inflection points. So I have all of the extrema and all of the inflection points. If I wanted to actually sketch the graph, all I'd have to do is plug these in and draw a nice pretty little picture with that. So I'm going to have you all try one out. Again, I'm going to have you try one of the authors. So f of x is x to the 4th plus 4x to the 3rd. So see if you can find critical numbers. Use the second derivative test. Or relative extrema. Let's see what else. Possible inflection points. Then test to see if they are inflection points, and then see if you can make a sketch. All right, so go ahead and pause that, see if you can run through those steps, and we'll finish that out together. Okay, welcome back. So we'll need f prime of x. We'll also need f double prime of x. F prime, 4x cubed plus 12x squared. f double prime of x, 12x squared plus 24. So our critical numbers are places where the first derivative is undefined or 0. This is a polynomial, so we're just going to have zeros. So 0 is 4x cubed plus 12x squared. We can do a little bit of factoring there. We can pull a 4x squared, leaving us an x plus 3. So x equals 0, x equals -3 are the critical numbers. So second derivative test, we're plugging those in and checking the concavity at those points, since these are places where we have a horizontal tangent line. So f double prime of 0 is 24. That is greater than 0, so concave up. So we have a horizontal tangent line, concave up. This is a relative min. F double prime of -3. We have 12 by 9 plus 24. That is also greater than 0, so that is also concave up. So we had a horizontal tangent line, concave up. So this one is a relative min. My apologies here. Hopefully you caught my error here. F double prime of x is 12x squared plus 24x. My apologies there. So that would not throw this off, but that will throw my values for the last two off. My apologies. So f double prime of 0 is 0. So the second derivative test fails here. So I don't know if this is a local max or a local min. It may be an inflection point though. So this will come up later. As far as our other critical number, the -3, f double prime of -3. We have 12 by 9 plus 24 by -3. F double prime of -3 then is 108 minus 72, which is greater than 0. So that is concave up. So horizontal tangent line, concave up. This is a relative min. So we definitely have one relative min. So we have our second derivative test. It worked one of the two times. Possible inflection points. For possible inflection points, we set the second derivative to 0. So 0 is 12x squared plus 24 times x. We can again factor that. So x equals 0 or x equals -2. So we have two possible inflection points. So then we'll cut the number line up and use test points. So we have the -2 and the 0. Recall from the previous page, f double prime of x, 12x squared plus 24x. So we'll try maybe x is equal to, yeah, we'll do just nice pretty numbers, -10, -1, and I don't know, 1. And we'll we'll see if we change concavity there. So f double prime of -10 is 12 times 100 plus 24 by -10. So that's 1200 minus 240. That is positive. So we're concave up on this interval. F double prime of -1. 12 by 1 plus 24 by -1. So that is a -12, less than 0, so concave down. So -2 definitely has an inflection point. Then we'll try the 1. So that one's worth 36, greater than 0, concave up. So both of those were inflection points. So then we just go back to the original to find the ordered pairs that go with them. So we know that we have a relative min at x equals, on the previous page, at x equals -3. Inflection points at x equals -2 and at x equals 0. And our original function, recall, f of x was x to the 4th plus 4x cubed. So to find where these are, I find f of -3. So let's see, that would be 81 plus 4 by 27. -27. So 81 minus 108. F of -3. And we're at -27 then. So -3, -27, local min. F of 0 is 0. So 0, 0 is an inflection point. And f of -2. Let's see, then we get 16 plus 4 by -8. So that's 16 minus 32, -16. So -2, -16. It's also an inflection point. And then we know about the concavity between those points as well. So we'll do just a nice little sketch here. -3, -27. We have a local min that was concave up. -2, -16. We have an inflection point, so we went from concave up, flattened out, and now we're concave down until we get to the 0, 0. And then we changed from concave down back to concave up. So that gives us sort of a reasonable, just quick, rough sketch hitting the highlights of what's happening with that graph. So some problems that I would recommend trying from section 4.2. I'd try out 9 to 16 all, 17 to 39 every other odd, and 53 to 73 also every other odd. Or you can try the equivalent in the electronic homework as well. If you have any questions, please come see me. Otherwise, I will see you next time. Stay safe out there.